We got two kinds of curved mirrors. What's this kind called? Two names to it. I don't care which one you give me. Yeah. Yeah, we can call it a converging mirror because rays of light converge as a result of this, of hitting this mirror. What's the other name that we give to it? Yeah. What's the other name that we give to it? Yeah, good. Concave or converging. Converging because rays of light converge. Concave because it's caved in the middle, thinner in the middle than it is at the edges. Now, this is what we call the principal axis. That's the exact same term that we give to the lens ray diagrams as well. This is our focal point. This is 2f. This is twice the distance from the mirror as the focal point is. But there's some more significance to that 2f point for mirrors that isn't there for curved lenses. What's the significance of 2f beyond it being twice the focal length of curved mirrors? Yeah, it's the radius. If you made this a complete circle, then that would be the radius. That would be smack dab in the center of that circle. All right. We're going to draw two of these ray diagrams. This is review because we've done all of these before here. First one, I'm going to put the object somewhere in here, anywhere in between f and 2f. There's two rays that we're going to draw here, right? First one is parallel to the principal axis. Where does it reflect? Where does it go? Dustin? It reflects down through the focal point, right? Down here somewhere. Okay, second ray goes from the top of the object. Remember, there's millions of rays of light here. We could draw any of them, any of them. It's just that these two are very predictable. So let's pick the ones that are easy, as opposed to the other million of them that are there and work, but are not so easy to draw. Where's the second one going to go? And where's that second one go? From the top of the object where? Down at an angle, yeah, what angle? It's got to have some significance to it, right? So if you think about it, like you recognizing that it's going down at an angle, okay, that's a step. But we're not going to draw it down at some random angle like this, right? It's got to go somewhere. 45 degrees? It could be 45 degrees, but not necessarily. So that's not what we're looking for there. Anybody else? Down at an angle where? Through the focal point. Now, where's it going to reflect? Aiden, you're up on this one. If we went parallel and then down through the focal point, down through the focal point is going to go. Yes. There it is. See, there's always a like a reasoning for everything, right? And that's what I'm trying to get at there, is that you don't necessarily have to, I mean, we're going to remember it, but we don't necessarily have to consciously try to remember it. It's a matter of just using some reasoning there, right? If the first one goes parallel through the focal point and the second one goes through the focal point, well, symmetrically it's going to go parallel, right? The image is formed right there. Characteristics, Brendan, what's one of them? It's inverted, good. What's another one, Kathleen? It's real. Solid lines intersect, which means it could be projected onto a screen. Third one, Aisha, what's the third one? It's enlarged, it's bigger. Yeah, good. Good. Okay, let's draw one more ray diagram for this. Let's put this one inside our focal length, really, really close to the mirror. Like that first picture that you saw when we introduced this concept a few days ago. First ray, we know that it goes parallel to the principal axis down to the focal point. Second ray goes where? This one can't go through the focal point. Focal point's behind it. This one goes away from, not towards, but away from 2F. Reflects off the mirror, goes back down this way. I shouldn't have drawn that as a dotted line, though. Solid line. Back down this way. They don't intersect. Let's extend them. They do intersect back here, which means that we have an image formed back here. What kind of an image is it? James, what kind of an image is it if dotted lines intersect? Good. Virtual image. Couldn't project it onto a screen even if we wanted to. Virtual image. Okay, what are the other two characteristics of the image? Macaulay, what's one of them? It's larger. Good. Aisha, I think, said it was enlarged. That's a term that your textbook uses. Yeah, I don't care whether you say it's larger, it's enlarged, it's bigger, it's larger. Okay, whatever means the same thing. Okay, your textbook says enlarged, you use whatever you want. Okay, it's bigger. The other characteristic, the other attribute is that it's upright. Got it? Okay. I asked you to draw the ray diagrams for our convex mirror or our diverging mirror, rays that diverge away from the focal point here. I asked you to do the last 3 of these, I believe it was, for homework. It doesn't matter where we put our object. We're going to get the same characteristics of the image. So we'll draw one of them, and we'll just put our object in a random place. Put it right here. First ray of light is going to go parallel to the principal axis. Where does it go from there? Where does it go from there? Yes. Yeah, it goes up this way, but how do you know exactly where to go? There, there. Second one? Yeah, that's pretty close. The significance of that is that it goes away from that focal point right there. Right? Now the second ray is going to go from the top of the object where? Where's that one going to go? Good, towards the focal point. But it can't make it all the way there because there's a mirror in the way, right? It goes toward that focal point right there. And it's going to reflect where? Good, parallel to the principal axis. They don't intersect. Let's extend the reflected portion of that wave, of that light. We're going to find that they converge back here as dotted lines. Characteristics here. Number 1, Aaron, what's one of the characteristics there? It's virtual because dotted lines intersect. You couldn't project it onto a screen if you wanted to. Okay. What's the second one? Reese, what's the second characteristic besides virtual? Jake? It's upright. Good. Obviously, we can see why it's upright there. And Luke, what's the third one? It's smaller than the object is. Okay, you would have drawn 5 ray diagrams, a couple of them in class, 3 of them for homework, for convex or diverging mirrors. All 5 of the mirrors should have produced these characteristics. Now, this image may have gotten a little bit bigger or smaller from diagram to diagram, but in every case, it was going to be smaller than the object was, and virtual and upright. Any questions on that? All right. We're not going to spend very much time on what I'm about to show you at all because you've effectively already done it. Mathematics of curved mirrors. This was my favorite slide to prepare in all of Physics 30. You know why? Because all I did was took the page that I had already made for curved lenses, copy it, Control-C, paste it, Control-V, and change the word lens to math. I mean, change the word lens to mirror. You know what I mean? The equations that we use for curved lenses were 1 over f is equal to 1 over do plus 1 over di, and m is equal to hi over ho equals negative di over do. They're the exact same 2 equations that I'm going to use for mirrors as well. All the variables mean the same thing. All the units are the same. What about sign conventions, positive and negative? Well, the first 3 variables, f, do, and di, are all associated, once again, just as they were with lenses, they're associated with real. So f is real if you have a real focal point. do is real if you have a real object. And di is real if you have a real image. Versus a virtual focal point, a virtual object, and a virtual image. This looks exactly the same as it did for lenses, right? It's the exact same table. When do you have a real focal point? Well, when it's a converging mirror or a converging lens for that matter. Virtual if you have a diverging mirror lens. When you have a real object, well, for us in Physics 30, it's always. There is a time, perhaps if you go on in physics beyond Physics 30, that you could have a virtual object, but it won't happen in Physics 30. DI, real image, draw your ray diagram and see. I think if you project it onto a screen, it's a real image. HO and HI, just like for lenses, HO and HI are positive or negative based on whether they're upright or inverted. HO is positive if it's an upright object, and HI is positive if it's an upright image. They're both negative if they're inverted. Again, exactly the same thing as we have with curved lenses. Finally, magnification, the last sentence will be exactly the same again. Magnification is positive if the object and image are on the same side of the principal axis. In other words, they're both right side up, M is positive. They're both upside down, M is negative. Sorry, M is positive in that case as well. Both right side up, positive M, both upside down, positive M. One is right side up, the other is upside down, then we've got a negative magnification. This page, even after I fill in the blanks there and write down the equations, is identical to the lens page except for the word mirror. We're going to do an example here, but it should go really, really quickly for us because not only have we done examples with lenses, we've also done practice questions with lenses. You guys should be able to nail this right off the top because it's exactly the same thing. Here's a problem on 664. It says an object is located 20 centimeters from a converging mirror. What does that tell us? Converging mirror. The word converging always tells us that F is real and therefore positive value. So this is going to be our focal length. I'm just going to make a note that it's positive. It's more important if you deal with one that's negative to make the note that it's negative, right? Because if you forget all about positive and negative, it's going to be positive by default. But it's never a bad idea to be in that habit of identifying whether it's positive or negative right from the beginning of the question. This is going to be DO, and DO is always positive for us. We're going to look for DI here, the image distance. Here we've got HO. We want to find HI. We want to find M. And then we want to find out whether it's right side up or upside down. You've got two things you can start with here. 1 over F, 1 over DO plus 1 over DI. M is equal to HI over HO, negative DI over DO. Cassie, which one do you want to start with here? Which one of those two equations do you want to start with? Okay, 1 over F. Doesn't matter, right? Pick one. If it doesn't work for you, try the other one. So let's say 1 over F, 1 over DO plus 1 over DI. We've got F, so let's say 1 over 15 equals 1 over 20 plus 1 over DI. That seems to work because there's only one unknown there. Let's pull out the calculator here. Let's say 15 x to the minus 1, subtract 20 x to the minus 1. 1 over 20 goes over by subtracting. Let's flip that over. We get DI is equal to 60. DI is 60 centimeters. Good? Looking for HI and M as well. Let's say HI over HO equals negative DI over DO. Solve for this one. What's that equal? 15? neg 15. And then finally, magnification. We need the attitude now. The attitude means right side up or upside down. Which is it? Oliver, can you tell which way it is? Upside down or right side down? How do you know? Because what's negative? Good. Now, assuming the object is right side up, a negative magnification tells us that the image is flipped over relative to the object. So one is above the axis, one is below the axis. Okay? If the object is above, then the image must be below. The other thing we can look at is HI directly. HI is negative 15, upside down. Lucas, you have a question? Okay, glad I could help. It's inverted. Good. Okay, I'm going to give you a few minutes to work on a couple questions in class, but not very much. Okay, about 6 minutes here till about 1:30 to work on the questions that go along with us on page 664. There's 5 of them, which means you're going to have a little bit of homework on this tonight, but they should, I think, go fairly quickly for you, so you should even get a couple of them done before I move on here today.